Hi everyone, I am Anirudh and this is my topic for the presentation for the course Introduction to Plastic Electronics. I have chosen the topic of Printed Operational Amplifier. Why this is an interesting question. I am going to give reasons for the same now. So printable electronics in the recent past has resulted in a paradigm shift that will be able to print electronic devices in air at room temperature. So this can help us in developing a disposable electronic path sensing system that can monitor health conditions and help in medical usage. So this is why this is interesting, the topic of printable electronics. And why operational amplifier? Again, the operational amplifier is the workhorse of modern day analog electronics, and there has been recent literature that supports the use of operational amplifiers in printable technologies. However, they have been found to work at very high voltages of greater than 40 volts. But this paper specifically discusses the operational amplifier that is made using a 5 volt supply, which can be obtained on chip using a simple battery and not using any DC-DC converter that converts 5 volt to 40 volt or something. So that is why this is interesting. And the usage of OPAMP in low voltage operation and its high versatility will open up the disposable electronic path system which I described. Uh, so the talk is organized as follows. So I'll first be talking about the fabrication of device that we are interested, the organic transistor, and we will then move on to characterizing the device, and then finally closing with packaging. This will end the section on devices. The second section I would discuss about how to design an operational amplifier and how to characterize its open loop and closed loop behavior. In the third section, we'll briefly visit circuits, and in the fourth section, we'll figure out what is the compact spice model for this operational amplifier. So, first section on device fabrication. So, as I mentioned previously, literature shows that there have been instances of printed operational amplifier, but not at low voltage operation. There has been operation beyond 40 volts. So the fabrication for this specific paper is done using printed technology. So printed electronics is manufactured by printing technologies such as inkjet printing and offset printing with electronically functional ink. And the advantage with printer technology is that you do not require any vacuum processing and enable direct patterning without any photolithography. So in this case, the OPAMP is built on a 700 micrometer thick glass substrate, which is cleaned in ultra pure water, and the insulator has been deposited in vacuum, and the printing here is done using a silver nanoparticle ink. So this is the first step which I will describe later on, and the fabrication is done using a solution process, and it is also very critical while fabricating that the p-type OTFT and the n-type OTFT have similar mobilities. That has been ensured by using some specific structure which we will look at later. And then the technology here uses blending. This again is done because recent studies have shown that blending reduces device to device variability. So this improves performance. So that is why blending has been done. And as I mentioned earlier, they use a silver nanoparticle ink to print. And the first step is to fabricate an n-type OTFT after placing the glass substrate and depositing the parylene insulator. So we use an air stable and soluble compound. Obviously, it makes most sense that you use an air stable and soluble compound because you would be using this sensor to the external world. And the electrodes are printed using the silver inkjet technology, and this parallel gate electric is deposited in vacuum. Once the parallel gate dielectric has been deposited, the N-type organic semiconductor is deposited. The N-type organic semiconductor is a thiazole derivative Tu3, which has been blended with poly alpha methyl styrene to reduce variability. The structure of the OTFT used here is a dual gate bottom contact device. And after the deposition of the organic semiconductor, this was annealed for 1 hour, and again parylene was deposited. And as you can see, the via contact here was made using yttrium aluminum garnet laser. And after again the deposition of parylene, the top silver electrode was also printed. And this N-type dual gate OTFT demonstrated a mobility of 0.04 centimeter square per volt second with a threshold voltage of 0.1 volt. And after the N-type OTFT was fabricated, the P-type OTFT was made. So again, the P-type OTFT was made using an air stable and soluble compound. Here the component used is anthradiethiophene derivative DIF-TES ADT, which was blended with polystyrene again to reduce variability. However, here it is a single gate device, bottom contact device, and this shows a mobility of 0.08 centimeter square per volt second and a threshold voltage of about 0.35 volt with a switch on voltage of around 0. And then after the fabrication of the P-type OTFT, the PTFE was deposited. And moving forward, this is the same diagram which I showed earlier, but just enlarged. And so what motivated the authors of the paper to move for a dual gate OTFT N-type over a single gate N-type OTFT? As you know, for an operational amplifier, there are two key determinants. The first thing is the subthreshold slope that determines how fast your transistors turn on or off depending on the voltage. And the second thing is the channel length modulation parameter. So channel length modulation parameter basically determines how much variability you will have in accumulation for an OTFT in current, and it also in some way it limits the maximum gain you can get from an amplifier. So that is also another critical parameter. So the authors of the paper fabricated the P-type single gate OTFT and also the N-type single gate OTFT. The subthreshold slope and the channel length modulation parameters were significantly higher for the single gate N-type OTFT compared to the double gate OTFT. So this became a serious concern. So because of this, the people who designed this moved to a double gate structure that resulted in a subthreshold slope of only 0.4 volt per decade and channel length modulation parameter of 0.005. And as you can see, the subthreshold slope and the channel length modulation parameter are more or less close to the P-type substrate. However, the mobility is slightly off, but this is not significant. So it is stated that the device simulations revealed that the improvement of the subthreshold slope and the channel length modulation parameter lambda were due to the suppression of the current flow at the bottom side of the channel, which was not controlled by only the top gate in case of a N-type device. So that is why the dual gate served its purpose. And the next step is, once the fabrication is done, you need to characterize your device. So you would characterize your device, you would sweep, you would get IDVG plots and IDVD plots, and as you would expect, these plots are similar to the OTFT characteristics which we have studied in class. So this just testifies that the device was working properly. moving forward, once you have designed and fabricated the device well, you need to package it to test it easily. So in this case, they use a dual inline packaging technique, DIP as they call, for easier prototyping. And the next section, we'll talk about how the op-amp was built and its characterization. So as you know, an op-amp is essentially a voltage controlled voltage source with a very high input impedance and a very low output impedance with a very high gain. Ideally, this gain A should be infinite for an ideal op-amp. And this is the structure of a two-stage op-amp which is used in the paper. So this terminal is external, so you can connect a current source to the external world between this node Cur and VSS, and this current would basically be mirrored from M1 to M2 and then to M3. So this acts like a current mirror stage, and this stage transistors M2, M4, M5, M6 and M7 constitute the single stage op-amp, and M3 and M8 form the second stage of the op-amp. So two-stage op-amp is used so that the loading effect of the second stage on the first stage can be limited. And as you can see, this op-amp is not compensated. This is because the poles are far apart. The dominant pole is determined by the output load capacitance. Thus, compensation is not necessary. Anyway, for a two-pole system, the system is always stable. It's unconditionally stable. And next step, once you have designed the operational amplifier, you would continue to characterize. The first characterization, as you know, is checking whether the op-amp works in open loop. So to check the characterization of the op-amp in open loop, a supply voltage of plus 2.5 volts was used for VDD and minus 2.5 volts was used for VSS. And as you know, the op-amp characteristic equation is V out is equal to A times V plus minus V minus. The area of the printed op-amp was 4.3 times 4.44 millimeter squared, and the bias current, which I described here between Cur and VSS, was set to 20 nanoampere. And this was the plots obtained in the paper. So as you can see, the open loop characteristics indicate a high gain in open loop, as it should be. Experimentally, it was determined the open loop gain was 60. So typical op-amp characteristic you would observe here. As you can see, there is some sort of a hysteresis. So this dotted black line shows the hysteresis because of only using a single gate n-type OTFT. As you can see, the area enclosed by this hysteresis curve is large, which shows that the op-amp was significantly slow, and this red curve shows the hysteresis for the dual gate op-amp, and as you can see, the area is much lesser here, which indicates faster operation. The switching voltage of the dual gate op-amp was plus 0.15 volt in the forward sweep and minus 0.04 in the backward sweep, and this was done at one particular V minus, and as V minus was swept between minus 2.5 and 2.5, the curve just shifted leftward or rightward as the case may be, which corresponds to ideal op-amp operation. And the next step is to check whether the op-amp works well in closed loop. So the first thing you would build in a closed loop is a buffer. A buffer is used to electrically isolate one component on chip from another component on chip. Theoretically, you would want your buffer to have a gain of 1, and experimentally it is calculated that this op-amp gives a gain of 0.99 and has an offset voltage of less than 50 millivolt, and you operating it in closed loop significantly reduces the hysteresis. And as you can see, as a function of input voltage, the buffer closed loop gain is more or less 1 throughout the range of operation. And the next step is to design a non-inverting amplifier. And as you know, this non-inverting amplifier circuit has a simple gain of 1 plus R2 by R1. And why a non-inverting amplifier? That is because if you want to amplify something, you would want to have good control over the gain. If you would use something like a common source amplifier with only one transistor, you would end up having dependence on mu, Cox, etc., which comes with significant variability, which is not desired. So you would use a non-inverting amplifier. So the paper mentions that if R1 and R2 were set equal to 100 mega ohm, the gain was about 1.8, and when R2 was set to be 1.1 giga ohm, the gain was about 8.2. Again, this is the closed loop gain. The maximum deviation from the theoretical gain is under 25%, and the frequency response is also a critical parameter. So as you know, the unity gain bandwidth is basically the frequency up to which you can use your op-amp, and that is 50 hertz. And as you know, the cutoff frequency for this transistors is proportional to the supply voltage. So under 5 volt operation, this 50 hertz is a significant improvement over previously cited papers. And the final part will discuss about circuits. So as you know, with operational amplifiers, you can implement various kinds of arithmetic circuits and signal processing applications, ranging from oscillators, comparators, and other things, to simple arithmetic operations such as integration, differentiation, summation, etc. So specifically here we will talk about integration and differentiation. So as you know, to use an op-amp as an integrator, you would use a resistor and a capacitor. So here they have used a 1 giga ohm resistor and a 1 nanofarad capacitor and given a square pulse input, and the integral of a square pulse is a triangular pulse. And as you can see, for an input square pulse, the output is a triangular wave as expected, and they use another differentiator. For a differentiator, you just switch the role of the resistor and the capacitor. So with that, it is very obvious that if you give a triangular wave to a differentiator, you would expect a square pulse. And this is the input triangular pulse shown in blue, and the expected ideal response was expected in this dotted black line. However, the red curve was the output, which more or less seems okay. And the next step was to check heavier or more complex operations, which includes a transimpedance amplifier and an oscillator. A transimpedance amplifier is basically something that converts a current to a voltage when you have the gain under control. This gain is exactly equal to the resistor you put in the path between the negative terminal and the output. That should be 1 giga ohm. So if you inject 1 nanoampere of current, you would expect about 1 volt at the output. So which more or less seems okay from this graph. And this TIA is very useful in biomedical sensors that take in current input and give voltage output. So that serves the purpose. And then an oscillator is used to generate clocks. So this is a complex looking circuitry of an oscillator. And this operational amplifier basically looks or behaves in a fashion similar to a conventional Smith trigger, and then it generates this sort of output waveform, irrespective of the input voltage, which is as expected. And the second stage basically behaves like a comparator that compares this V in and this V out one, and then gives a square pulse at the output. So in the last section, we will briefly look at the SPICE model for the op-amp, the OTFT, how we'd model in SPICE. So as you know, these are standard MOS modeling parameters: the length, the width, the mobility, the oxide thickness, the VTO, that is threshold voltage at zero bias, and VGSO is the gate source overlap capacitance, and VGDO is the gate drain overlap capacitance. Lambda is the channel length modulation parameter. So these things have been picked purely based on fitting the data. These are not related to the actual parameters obtained experimentally. So As you can see, the channel length modulation parameter is slightly off, 0.012 against 0.016. This more or less matches. And T-aux is in a sense not appropriate because we don't use explicitly an oxide layer, but it's more or less similar to a dielectric layer here. And mu naught basically is the low field electron mobility. Both of them are equal to the value 0.07 centimeter square per volt second. But this is not the exact value that was calculated experimentally. And these are solely obtained for the sake of simulation. And I would like to cite the references I have used. The first reference from which more or less the talk has been taken from is Printed 5-volt organic amplifiers for various signal processing operations by H Matsui et al. From Tokyo. And the second is a standard text on analog electronics, microelectronic circuits by Cedar and Smith. So, thank you.